Hi everybody, welcome to another video on Discrete Math section 1.4 Predicate and Quantifiers. So earlier we have proposition and we can make each of them a proposition. However, there's some idea of linking the concept of properties of being a man or being model, those kind of things. So in that case, proposition is not enough. There must be a way to address this. And the way to do that is the predicate logic. So the variables x, y, z and the proposition, or in this case the predicate p of x, f of x, that is depends on whenever we substitute x into this, it's kind of like a function. But this was just a logic, it carries the value true or false. And after that we will have quantifiers to go with it. Propositional function generalization of proposition. They contain variables and the predicate. Variable can be replaced by elements from their domain. Right, so we have p of x, pretty much like function. And then we can substitute the value of x into it. And because we have the domain. This book kind of backward. So we don't have any symbol for the set theory yet. But if you take in all the math class, they address the set theory before this. But regardless, we write p of x to denote a propositional function p at x. So here's some example. If we say p of x denote x greater than 0 and the domain are integers. Right. By the way, if we have a set theory, the integers denote by z, the boldface z. And if we say x is an integer, we just simply say x is in the set of integer. Right. Like that. But we study set theory after this chapter, so it's kind of backward. But we can write like that. Anyway, so p of x denote x greater than 0. So now if we have p of negative 3, so what we do is we substitute negative 3 into x, so it's just like a function, right? So negative 3 greater than 0, and of course that is false. And then p of 0, just put 0, and of course that also false. P of 3 greater than 0, so that is true. So just like function, we substitute the values into x, or whatever the variable is, and then we can determine if it's true or false. It can only carry values true or false, unlike general function. Right, often the domain is denote u, so this case u is the set of all integers. Right, now let x plus y equal to z be denote the relation or R of x, y, z for u on 3 variables, be integers. Find the true values. So simple enough, we substitute first one for x, the second one for z, for y, and the third one for z. So that 2 plus negative 1 is that equal to 5, and of course this is false. Next, the first one for x, the second one for y, and the third one for z, and this is true. And then x plus 3 equal to z, and this case we don't know, so we'll just say depends on x and z. Right. Quantifiers. We need quantifiers to express the meaning of the English word, including all or some. So we say all men are mortal, or some cats do not have fur. So the key word to focus here is all or some, and of course other maybe could be none or many or at least one. There's a lot of things, but all and none are classified in one type of things, and some, many, at least one, and those classified in something else. So there will be 2 type of quantifiers The first one is universal quantifiers, denoted by the upside down A, and denote meaning for all. But like I said, it could be none, it could be all, and every, those kind of things. And then the existential quantifiers is the kind of backward A, mean they exist. So like I said, the universal including all or none, and existential anything in between should be at least one, many, some, that is neither all or nothing. Anything in between is existential. On the extreme, all or nothing, that is universal. However, the none and all have different meaning. The none have the negative meaning compared to the all. We talk about that later. First, we define the universal quantification of p of x, or we call the universal quantifiers. We write like this: for every x, p of x. And the upside down A is called the universal quantifiers, and it is read for all x, p of x, or for every x, p of x. An element for which p of x is false is called the counterexample of that. Right. So let's look at some example. If p of x denote x greater than 0 and u is the set of integers, once again integers is this set of all the negative zero and all the positive. Of course, some of this are negative. So if you put the negative numbers in here, the statement is false. So if we say all of them, every x is going to be greater than 0, it's going to be false, because some values, when you substitute in here, is false. It does not true for everything, right? It does not true for every x. Therefore, if we write for every x, this will be false. Next, if we define only for positive, and because if it's positive, that works out perfectly here. So all the positive integers, if we substitute to x here, the equation, in the inequality is true. So in this context, if we talk about the positive integers, then every x is greater than 0, and this is true. And then the next one, for every x, x plus 1 greater than x, and it's true for domain of all real numbers. That makes sense because x plus 1 is bigger than x. Right? Any number plus 1 is going to be bigger than itself originally. So in this case, this is true. Again, if we had known about the set theory, we just say for every x in the real number, in the set of real numbers, we just write like that. But this is true, because x plus 1 is greater than x. Any number plus 1 is greater than itself originally. So that makes sense, right? So that is, we have the universal quantifier. Next, we define existential quantifiers. Existential quantifiers is like that. The backward A, if you will. That means is there exists an element in the domain such that p of x. Right. So there exists an element. So there could be one element, could be a lot of elements. But like that, it could be anywhere between 0, anywhere between none, and all. Between 0 and between nothing and everything. Anything in between is existential quantifiers. Right, so in that case we say there exists one element. So that is existential quantifiers. So let's look at some example. If we say p of x denote x greater than 0, so the same thing as before, right? Now we do have the for integers, but this time it is existential. So there exists an x such that p of x, meaning if I spell this out, there exists an element X in the domain such that p of x in this case greater than 0. So there exists an element X in the domain such that x greater than 0. So, and of course the set of integers, they have some positive, so there at least one element that works, so it works. Of course it also works if the domain is all positive integers, that certainly works. Like I said, we only need at least one is good enough. Now if we say if p of x denote x less than 0, and this time less than 0, and we only picking from positive, of course all the positive number will not less than 0, so in this case there is none, we make p of x true. There's no positive number will be less than 0, so therefore this is false, because this say at least one, that's not enough. It's false because there's none, not at least one. And for every x in real numbers, x equal to x plus 1 is false. That of course that's false, because there's no x that satisfies this condition. So there's no x equal to x plus 1. Here we write at least 1, so that's why it's not true. Right. Of course we can also define existential but unique with the exclamation point here. So we said there exists unique x, there exists exactly one value of x such that p of x. So there's one and only one x in the universe of this course, meaning in the domain. Or we said there is a unique x such that p of x. Right, p of x is whatever we define to be. Right, here more example on quantifiers. The true values of existential quantifiers or universal quantifiers depend on the proposition and on the domain. So depends on what is the function and what is the domain. Right, precedent of quantifiers, so like order operation, always these two first before any logical operators. So we have the quantifiers and then negation and then everything. So let me say that again. Quantifiers, negation, conjunction, disjunction, and then conditional, biconditional. So that is the order. Right, here we have a couple of examples here. It said translate the following to predicate logic. Every student in this class has taken a course in Java. So if you is all student in this class, define j of x denote x has taken Java. So we translate everybody in this class has taken Java. Right. Now, but if u is all the people, if we write u is all everybody, proposition denote x is the student in this class and translate like that. So if it is the student in this class, it is taken Java. So yeah, that makes sense. Next, translate the following sentence in the predicate. Logic. Some student in this class has taken a course in Java. So we say there exists some student in this class, which is you, taken Java. So that's one good. But if we write if use all the people, then translate all the students in the class, everybody in this class in Java. So this is kind of with in this class and taking Java. So yeah, so that is different of the two. Next, what the following statement means. uh, for every x less than 0, x squared greater than 0. So we say, let's just spell this out. This means for every x in the domain, whatever the domain is, x squared greater than 0. For every x less than 0. And then we say every y not equal to 0, y cube is not equal to 0. For every y not equal to 0 in the domain, y cube not equal to 0. And then there exists an element z such that z squared equal to 2. The comma here can be replaced by such that. Next, logical equivalence involving quantifiers. Right. Once again, we use this to denote logical equivalence. Right. Now, if we have the predicates and quantifiers, it is equivalent if and only if they have the same true values for every element in the domain. And of course, for every variable in the expression. So this is for every predicate substitute into this statement and for every domain used for the variable in the expression. So we have to true for every values x. Now quantifiers as conjunction and disjunction. So if we write for every x p of x, meaning that if it is for every, it's going to be n. And if there exists, it's going to be all. Meaning that when there exists, we only need one of these to be true. Whereas we write this for every, meaning have to be true for every p of xi. It have to be true for every p of x, true for every value of x. Right. Negation of the quantified expression. So this is the De Morgan's law. So we said the negation of, so when we try to write the negation of the quantified statement, first we will negate, we turn the existential into a universal, or from a universal to existential, and we have to negate the statement. So two things, interchange quantifiers and negate the predicate to say effects. So we have to do two things there. Right. So here's an example of that. Once upon a time, there was a member of parliament got in trouble by saying, so what he means, what he says is, half of the members of parliament are idiots. So he focused on the quantifiers of half. And because when they say that, he got into trouble and he had to issue an apology. And his apology is this. What I meant to say was half of the parliament are not idiots. So he did negate his statement by throwing the not in there. However, this is not true. I mean, it's not really the negation of the whole statement because they still have. So we did not change the quantifiers. So that completely doesn't change any meaning. We do not mean negation at all. So think about this. If half of them are not idiot, maybe the other half is still idiot, right? So that's why when we want to negate a quantified statement, do two things. Interchange the quantifiers universal to existential or existential to universal, and then we negate the predicate, right? So like I said, the problem here is this have to be changed to something. So if the true apology, I mean, if we want to say opposite to what he said earlier, he should say that what he meant to say was all are not idiot. So that is the true negation of that statement. So we throw in not to negate the statement, and we interchange from existential to universal. So that is the true negation there. Right. Now, write the negation for the following statement. Every student in your class has taken a course in Java. Right. So we just focus on two things. Every. So in that case, we change to existential. Existential could be a lot, many, some, there exists at least one. Any of those is fine. But just say some. So we interchange the quantifiers, and then the rest. Some student in your class has not. Just throw that in, so we have the negation of the statement. Taken a course in Java. So two things, quantifiers and negated statement. Right. Many people in Dallas are Cowboys fans. If we want the negation of that, we turn many quantifiers. This is existential. Now we turn to all people in Dallas are not Cowboys fans. So we have to change the quantifier and then negate. Right, we can also write, instead of all, we can use none, which is another quantifier. However, the none has the negative meaning to it, so we don't have to write not if this is the case. So we say none in Dallas are Cowboys fan. So this is the negation of the statement before. Right. So when we change the quantifiers and negate the statement, we have the negation of the quantifying statement. Right. This is for every x squared greater than x. So we have to change everything. First, universal to existential, and this so it's not greater than, have to be less than or equal to. There. So we negate two things, negate and then change the quantifiers. There exists an x such that x squared equal to 2. So we need to change that to for every x, and then we just say not equal to. So yeah, do two things, negate the statement, change the quantifiers. Next, every student. So that case we change to some or at least one. At least one student in this class. Has visited Canada or Mexico. Okay, so has not visited or Mexico. Actually, when we write like that, if we put the parentheses around it, that's fine. But if we don't have the parentheses, we have to change this to n. Yeah. So, if you write the reason of that is have not visited Canada and not visited Mexico. I guess if we don't need the parentheses, then we'll just leave it all. I'll be just fine. Yeah, just leave it all. Right. So, if you write this as the logic, every student in the class has visited or Canada or Mexico. Now it's nice to write like that, right? Now we change to existential, and then we have negate of the whole thing here. Okay, if we write like that. However, the De Morgan's law, this will turn into not C and not Mexico. So, if we want to do it precisely, we can say it. Okay, should we write like that? I've run out of space here, so I should say it. This is equal to not Canada, and the Morgan's law say we have to turn that upside down, not Mexico. Right. Should we write it out, it's going to be like this. So proper way to say this exactly is at least one student or many or some student in this class has not visited Canada and has not visited Mexico, and it's going to be n, and the logic of that is the De Morgan's law. So it should be saying like this. So that's proper way. So once again, at least one student in this class has not visited Canada and has not visited Mexico. So we write like that. So it's more precise statement than that. So we don't have the parentheses basically. So it's better to remove the parentheses, use De Morgan's law, and that's how it works. Right, that is that one. Next shows that this one is equivalent to that. So simply we just do the negation of everything. Right, so first, last time we did say that the implication is equivalent to say in not P of X. Or Q of X, right? So that is what the indication equivalent to. So let's write more precisely. We said not negation of every x, p of x imply q of x. So first we'll replace inside the parentheses here. By the way, when we write like this, we mean the negation of the whole thing here. Yeah. So we replace inside this parentheses by this. That is standard implication. Right. Next, if we want to negate, we have to negate the quantifiers. Don't put the x in the parentheses like that. So negate the step quantifier statement by changing the quantifiers, and then negate what inside. Right. Now we distribute this into and using the De Morgan's law. So we have negation of p of x. And then remember De Morgan's law, we have to change the conjunction to disjunction and disjunction to conjunction, right? And then we have negation of q of x. And finally, negation of negation is the statement itself. So this gets back to there exists an x such that p of x and not q of x. So that's exactly what we have there. Right? So step by step, first replace the conditional by that. And then we have interchange the quantifiers and negate the statement. Negate the statement, we use De Morgan's law, change the sign of conjunction and disjunction. And then negation is the statement itself. So that's what we have. And with that, we finish section 1.4. As always, thank you for watching and see you in another video in Discrete Math.